Welcome to the Section 2 notes on matrices. This is all about determinants. And a determinant is just a mathematical process. Once you get the process down, it shouldn't be a big deal. However, a 2 by 2 matrix, which is what the first two examples are just plain easy. And anything beyond that, it does get a little bit weird. But again, memorize the procedure, you'll be fine. So for starters, we need to point out that a determinant can only be done or configured if you have an even number of rows and columns. So in other words, you can do a 2 by 2 matrix, a 3 by 3, a 4 by 4, etc., etc. Excuse me, but rows and columns must be the same number. So here's how we figure out a determinant. You multiply the right-facing diagonal. I'm going to abbreviate, and then subtract what you get if you multiply the left-facing diagonals, which in a 2 by 2 matrix is pretty easy if you think about it, and here's why. There is a diagonal that goes that way, and that's the right diagonal. And there's a diagonal that goes that way, and I drew that line to the left, so that's a left-facing diagonal. So, right diagonal, -2 and 8. So we multiply those together, and then we subtract the other diagonal, which was a 5 times a 6, and that's it. That's a determinant. So pick up a calculator if you want. That's -16. That's 30. Subtract them, and you got -46. There's your determinant. Now, another thing that's important, which I forgot to point out at the beginning, you will notice that the symbols around the numbers are a little bit different. So from section 1, we said a matrix gets written with brackets. And that implies you're going to do some of the operations we did in the first video. So add, subtract, distributive property, multiply, etc., etc. But if they are looking for a determinant, they're going to leave the little hooks off the brackets. And it will be tempting to say that this is absolute value, but it's not. And if you're thinking to yourself, why is it that math always has to have different meanings for different symbols? I agree with you. Not sure why. But when you're talking about a matrix, so as far as an ACT test, they might, or some mathematicians will actually put DET for determinant, like, hey, figure me a determinant. And if you knew that's what you were doing, the process we just did to get to -46, pretty darn easy. But more often than not, you're not going to be that lucky, and on an ACT test, they're just going to put these straight up and down lines. So that stands for determinant. So please try to commit that to memory. So number 2, the fact that we have that absolute value looking symbol, again, it's not. That means I'm supposed to do a determinant. And if I'm doing a determinant, I do the, come on, right diagonal. So we'll just go ahead and write that now. That's 18. So we multiply the diagonals times 22. And then we subtract the left diagonal, which was -11 times -5. All right, what's 18 times 22? Well, I'm pretty sure that's 396. If I'm wrong, I apologize, because I just did that in my head. And then subtract. Now be careful, right? I got a whole bunch of negative signs going here. So we got to do the multiplication first. So -11 times -5 is 55. Now I'm supposed to subtract those. And if I subtract them, let's see, 6 minus 5 is 1. 9 minus 5 is 4. 3 minus nothing is 3. So my determinant for that second problem is 341. So as you can see, a 2 by 2 matrix only has one diagonal going each way. So we got a left diagonal, and we got a right diagonal. And those are easily done. So unfortunately, 3 by 3 matrices, not so much. Now here's what they mean by diagonal, though. So if I do a right diagonal, I'm going there. But isn't this sort of a right diagonal? And it is. But you do need three numbers, so it would be 1 times 5 times something. And when I was originally taught this in high school, my teacher taught it as a wraparound thing. So you would wrap it back around and get this 2. I'll show you a little different way here in a second, and it's easier. But the -2 also could be thought of as a diagonal. So if you wrapped it around, it would wrap around to the -4 and the 7. So if that seemed a little confusing, let me go ahead and give you a better way of doing it. But anyway, I was trying to point out, excuse me, there's more than one diagonal. So to me, the best way to go is this. What you want to do is rewrite the first 2 columns. So there's that first column. And 1, 2, 7, there's the second column. Now I actually have 3 diagonals. So over here in the box, it tells you what to do, which is that you're going to have to add up all the diagonals that go right, all the diagonals that go left, and then subtract them like we did in the previous 2 problems. So see if we can get one of these done, save the other one for video number 2. So that's a right diagonal. So that would be 3 times 2 times -1. But then we have to add up all the right diagonals. So rewriting those numbers makes it a little bit easier to find your diagonals. So now I get the 1 and the 5. And I don't have to wrap it around. I get that 2 right there. I got it. Plus the -2 makes another right diagonal. So -2 times -4 times 7. Okay, that's the right diagonals. Left diagonals. So we would start it off like we did the other one. So that's -2 times 2 times 2 plus. So again, if you write those numbers or repeat those numbers, it makes it easy to find that left diagonal that goes all the way across. I got a 3 times a 5 times a 7 plus, here's the third one. So 1 times -4 times -1. So the bad news is it's a lot to set up. The good news is once you have got it set up, you just need to pick up a calculator and do it. So let's see if I can't do this in my head here. So this first one, that guy will be a -6 plus 1 times 5 times 2 is 10 plus -2 times -4 is 8. 8 times 7 is 56. And if I add those up, let's see, 66, that would be 60. Use a calculator. The other ones, well, multiply all those 2's together, you get -8. 3 times 7 is 21. 21 times 5 is 105. So again, we're adding up all the left-facing diagonals. 1 times -4 times -1 will be +4. If I add those guys up, 109, I get 101. So we do the same exact thing that we did on the previous problem, only it was a heck of a lot more work to get to it. So this 60 was the total of the right diagonals. This 101 was the total of the left diagonals. And we subtract the diagonals. So that's what we did in the first problem, but only one diagonal to worry about. So 60 minus 101 is -41. And that's your determinant. But again, it's like anything else mathematically. If you can figure out the process, if you're comfortable with doing the process, then man, this is just like picking up a calculator, or literally picking up a calculator and getting yourself an easy answer. So it's a little bit of writing, but not too bad. All right, there is one more to try, one more example, and there's also a word problem in part 2 video, so check those out.